Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module R&D on photovoltaic or solar cell from the paper Nanoscience and Nanotechnology. So students, let us see what we are going to learn in this module. In this module, the working of solar cell is explained. Also, the various parameters which influence the efficiency of solar cell are discussed in this module. In addition, the timeline of the development of material for solar cells is discussed in this module. Finally, the classification of solar cells is demonstrated and various materials for solar cell production are studied. A solar or a photovoltaic cell, also known as solar battery, is an electrical device which is used to convert energy from light into electrical energy. The working of solar cell is based on the photovoltaic effect. This is a physico-chemical process. It is a type of photoelectric cell which can be described as the device whose electrical properties, for example, resistance, current, etc., change as light is exposed onto it. Large-scale photovoltaic modules are termed as solar panels and are made up of numerous solar cells. Regardless of the source, whether sunlight or artificial light, solar cells are termed as photovoltaic. They can be used as photodetectors to detect light, or we can say any electromagnetic wave in the visible range. Examples include infrared detectors. Besides, solar cells can also be used to measure the intensity of light which is incident on them. A photovoltaic cell operates on the following three attributes. First, excitons or electron-hole pairs are generated upon absorption of light. The charge carriers are separated as electrons and holes. Then the separated charge carriers are collected at the respective electrodes. That is, electrons move towards the positive electrode and holes move towards the negative electrode. In addition to this, a solar thermal collector can be used for direct heating or indirect generation of electrical power from the heat generated. In these devices, heat is supplied when sunlight is absorbed. Further, a photoelectrolytic or photoelectrochemical cell is either a type of photovoltaic cell which is similar to dye-sensitized solar cells developed by Edmund Becquerel, or a device which directly splits water into its constituent hydrogen and oxygen by using solar irradiation. Figure 1 shows a traditional solar panel which is made up of silicon. Electrical contacts, that is, silver-colored strips, are printed on the wafer itself. The working of a solar cell can be summarized as shown in the figure. Photons present in sunlight hitting the solar panel are absorbed by the material of the panel, for example, silicon. Now, the absorption of photons leads to the excitation of electrons from the atomic or molecular orbitals. Now, upon excitation, the electron either dissipates energy as heat and returns to its previous orbital, or it travels through the cell to be collected at the electrode. A counter current flows through the material to cancel the potential which is developed by this extra electron. This current is captured as electricity. The nature of chemical bonds of the material are crucial in this process. Most common used material is silicon, which is used in two layers. One layer is doped with boron and the other by phosphorus. The chemical electric charges in the two layers are different and subsequently both drive and direct the current of electrons. An array of solar cells is used to convert solar energy into a usable amount of electricity which is in DC form. Most common solar cell comprises a silicon-based large area PN junction. Other variants of solar cells include organic, dye-sensitized, perovskite, quantum dot solar cells, etc. To allow light into the active material and for collecting the generated carriers, a transparent conductive film is usually coated on the illuminated side of the solar cell. Films deposited usually have high transmittance as well as high electronic conductivity. For example, ITO, conducting polymers, conductive networks of nanowires, etc. Figure shows the Shockley-Queisser limit for theoretical maximum efficiency of a solar cell. Semiconductors having band gap from 1.5 electron volt, that is in the range of NIR light, have highest efficiencies among single junction solar cells. Multi-junction cells may have higher efficiencies. The solar cell efficiency constitutes various efficiencies. The first one is the reflectance efficiency, another is the thermodynamic efficiency, then the separation of efficiency, which is due to the separation of charge carriers, and fourth is the conductive efficiency. The product of these components gives the overall efficiency of the cell. The solar cell efficiency depends upon voltage, temperature coefficients, and allowed shadow angles. However, the measurement of these factors is complex. To alleviate this problem, various other parameters are calculated, and these parameters are used to determine the above mentioned factors. These parameters include the thermodynamic efficiency, quantum efficiency, integrated quantum efficiency, open circuit voltage ratio, that is VOC, and the fill factor. Quantum efficiency accounts for the reflectance and recombination losses, VOC ratio, as well as the fill factor. Resistive losses affect the fill factor, quantum efficiency, as well as open circuit voltage ratio. Fill factor, a very crucial parameter in performance of the cell, can be obtained as the ratio of actual maximum power obtained to the product of open circuit voltage and closed circuit current. The efficiency of single junction, that is PN junction silicon cells, has now reached approximately 33.16%. That is the Shockley-Queisser limit. For infinite layers of single junction cells, the efficiency can theoretically reach approximately 86% by the concentrated sunlight. Figure 3 shows the projected timeline for solar cell efficiencies, which is as given by the National Renewable Energy Laboratory. We will next discuss the timeline of development of material. Usually, the solar cells are named after the semiconductor material which is used for the production. The material used for creating solar cell must be able to absorb sunlight. Solar cells can be configured to either capture sunlight reaching the surface of Earth or work in space. Additionally, both single layer, that is single junction, or multiple layers, that is multi-junctions of the material can be used to produce solar cells. Figure 4 shows the global market share of photovoltaic technology. We can see that in earlier years, around 1990s, thin film was most successful in obtaining high efficiencies. Let us now study the classification of solar cells. Solar cells are classified into various generations. Firstly is the first generation cells. These are the conventional or traditional wafer-based cells which are produced from crystalline silicon. These are the dominant commercially available photovoltaic cells and uses polysilicon and single crystal silicon. Now coming on to the second generation cells, these include thin film solar cells made up of amorphous silicon, cadmium telluride, etc. These are commercially used in photovoltaic power plants, small standalone power systems, etc. Third generation cells, these include various thin film technologies and these are the future generation photovoltaics. Majority of them are at experimental stage and are not commercially available. These cells use both organic, example organometallic, as well as inorganic materials. Although at this stage they have poor absorption and low efficiencies, they are investigated for the potential of producing highly efficient and economic solar cells. We will now briefly discuss the various materials which are used for solar cell production. The first one is the crystalline silicon, that is C silicon. Crystalline silicon or C silicon is the most commonly used bulk material for producing solar cells. It is also termed as solar grade silicon. Depending upon the crystallinity and crystal size, bulk silicon is separated in multiple categories. The cells use the concept of p-n junction. Typical wafers which are used in solar cell production are 160 to 240 mm thick. Next we move on to monocrystalline silicon, that is monosilicon. These are more efficient and more costly than other types of cells. The cell's corners appear clipped like an octagon as the wafer material is cut from cylindrical ingots which are usually grown via Czochralski method. Solar panels using monosilicon cells are characterized by a distinctive pattern of small white diamonds. Coming on to epitaxial silicon, epitaxial wafers of crystalline silicon can be grown over monocrystalline silicon seed wafer via chemical vapor deposition process. After growth, these wafers are detachable as self-standing wafers of controlled thickness. The efficiencies of solar cells produced from these wafers are comparable to that of wafer cut cells. However, they are much cheaper when the CVD is performed at atmospheric pressures. The light absorption can be enhanced by tailoring the surface of epitaxial wafers. Polycrystalline or multicrystalline silicon, that is multisilicon, is also used for development of solar cells. These are made from cast square ingots, which are large blocks of molten silicon, cautiously cooled and solidified. Due to the presence of multiple small crystals, they are characterized by metal flake effects. These are low cost and most common type of cells. However, they have lower efficiency than the monocrystalline type. Next one is the ribbon silicon. It is a type of polycrystalline silicon which is produced by drawing flat thin films from molten silicon. It is cheaper than polycrystalline silicon. Additionally, silicon waste is greatly reduced since sawing from ingots is not required. Their efficiency is usually poor. Now, monolike or multi-silicon, that is MLM silicon. This is also known as cast mono. Small mono material is placed as seeds in polycrystalline casting reactors. The grown crystal is similar to mono material. However, the edges are polycrystalline. After slicing, inner portions are high efficiency mono-like materials. However, these are square and not clipped, while the edges are polycrystalline. This processing produces mono-like cells at the cost of poly. Next is thin films. The amount of active material is greatly reduced in thin film cells. Most common configurations involve sandwiching the active material between two glass panes. For comparison, silicon solar panels use single glass pane. This makes thin film cells around 2 times heavier than silicon panels. However, the ecological impact estimated by analyzing life cycle of thin film based cells is smaller. Cadmium telluride CDTE. It is the only thin film material which is comparable to silicon in terms of cost per watt. Nonetheless, cadmium is highly toxic and tellurium is rare. 1 square meter of cadmium telluride contains approximately the same amount of cadmium as a single C-cell nickel-cadmium battery in a more stable and less soluble form. Copper indium gallium selenide, that is CIGS, is another material which is used for solar cell development. It is a direct bandgap material with highest efficiency, about 20% among commercially important thin film materials. Typical synthesis technique involves vacuum processing such as co-evaporation and sputtering. This makes them costly. Researchers at IBM and nanosolar are trying to decrease the synthesis cost by using non-vacuum solution based techniques. Let us now discuss about silicon thin film. Thin films of silicon are typically deposited via chemical vapor deposition, example PECVD, by using silane and hydrogen gases as precursors. Various types of thin films can be grown by controlling the process parameters. These include amorphous silicon, that is ASI or A silicon edge, proto or nanocrystalline silicon, also termed as microcrystalline silicon. Among these, A-silicon is a well-developed thin film technology. A-silicon solar cell is produced from non-crystalline or microcrystalline silicon. The band gap of silicon, that is 1.7 electron volt, is higher than that of C-silicon, which is 1.1 electron volt. Therefore, visible portion of solar radiation is more strongly absorbed by A-type silicon than infrared portion, which has higher power density. Thin film A-type silicon solar cells are produced by depositing a thin silicon layer on a glass substrate via PECVD. Protocrystalline silicon, having percentage of nanocrystalline silicon, is most suitable for high open circuit voltage. The band gap of nanocrystalline silicon is similar to C-silicon. Therefore, both nanocrystalline silicon and A-silicon can be joined to form multi-junction or tandem cells, wherein top A-silicon layer absorbs light in visible range and IR is absorbed by the second or bottom nanocrystalline silicon layer. Let us discuss the application of gallium arsenide thin films in the field of development of solar cells. When used as thin film solar cells, single crystal gallium arsenide cells possess the highest efficiency, that is 28.8% among thin film single junction cells. However, they are very expensive and are generally used in multi-junction cells for concentrated photovoltaics, that is CPV, HCPV, and in solar panels for spacecrafts. Then about perovskite solar cells. These cells contain perovskite structured materials as active layer. Most often, it is a solution processed hybrid organic inorganic tin or lead halide based material. Originally, they had very low efficiencies, that is less than 5% in 2009, which are now being enhanced up to 20% as of 2014. They represent a very rapidly advancing technology among solar cells. They are extremely attractive for commercialization owing to the lower costs which are involved in scaling up their production. Next material which is attractive for solar cells is the light absorbing dyes. Dye-sensitized solar cells are produced from low-cost materials and no elaborate production equipment is needed. They can be formed as flexible sheets. Even though they do not have the highest efficiencies among thin-film solar cells, the price per performance ratio is substantially high, allowing them to rival the electricity generation via fossil fuels. Coming on to quantum dot solar cells are based on Grätzel cell, that is GSSC architecture. However, they use low band gap semiconductor quantum dots. For example, cadmium sulfide, cadmium selenide, antimony 253, etc., as light absorbers rather than using organic or organometallic dyes. The size of the quantum dots strongly influences their band gap. Additionally, quantum dots possess high extinction coefficients and are also able to generate multiple excitons per photon absorption. A quantum dot solar cell includes a mesoporous TiO2 layer as backbone of the cell, which is similar to dye-sensitized solar cell. This layer is made photoactive by depositing quantum dots over it via chemical part depositions, or electrophoretic deposition, or successive ionic layer adsorption and reaction. The efficiency is greater than 5% for liquid junction as well as solid state cells. By depositing both TiO2 and quantum dot layers in a single step, the cost can be reduced. This has been achieved by depositing a conducting solar paint made up of TiO2 and cadmium selenide onto any conducting surface. Nonetheless, though quantum dots have poor room temperature absorptions in quantum dot solar cells. To overcome this issue, plasmonic nanoparticles such as nanostars can be used. In addition to this, infrared pumping sources can be used to excite interband as well as intraband transitions in quantum dots. Coming on to organic or polymer solar cells, organic and polymer solar cells are made from thin films approximately 100 nanometers of semiconductors including polymers. For example, polyphenylene vinylene and compounds of small molecules such as copper phthalocyanine, a blue-green organic pigment, and carbon fullerenes and their derivatives like PCBM. They can be processed from liquid solution, providing the benefits of a simple roll-to-roll printing process, resulting in low cost and mass production. Further, these cells could be beneficial for such applications relying on mechanical flexibility and disposability. Presently, these cells have poor efficiencies and no commercial device is available. Let us next discuss about the cells, module, panels and systems. Solar modules are assemblies of solar cells and produce electrical power from solar light. They are different from solar thermal module or solar hot water panel. A solar array produces solar power using solar energy. Figure 5 shows a schematic of the components of a photovoltaic system. We can see in the figure how we can move from a solar cell to a photovoltaic system. Solar cell leads to solar modules. Solar modules leads to the generation of solar panel. Solar panel can in turn form a solar array leading to the development of a photovoltaic system. Solar photovoltaic panel or module constitutes a group of several solar cells which are oriented in one plane. These modules have a glass sheet on the illumination side which protects the active material and also allows light to pass through it and reach the active material. Solar cells are connected in such manner that the overall voltage is the sum total of individual voltages. Table lists the prices of most popular photovoltaic systems in US dollars. So we can see that the residential photovoltaic systems are the costliest in United States, followed by Japan and France, whereas utility scale solar cells also follow the same trend. The lowest price for the commercial photovoltaic system is in China which also offers the lowest priced residential and utility scale photovoltaic system. We will next discuss the timeline of solar cell development. Edmund Becquerel was the first to demonstrate photovoltaic effect in 1839 when he made a photovoltaic cell. In 1873, Willoughby Smith explained the impact of light on selenium while electric current was passed through it. First solid-state photovoltaic cell was developed by Charles Fritz in 1883. In this, he deposited thin gold layer on selenium to create junctions. This device has an efficiency of approximately 1%. In 1887, outer photoelectric effect was described by Heinrich Hertz, and first cell based on this effect was proposed by Alexander Stoletov in 1888. In 1905, Albert Einstein proposed quantum theory of light and explained the photoelectric effect. For this work, he was awarded Physics Nobel Prize in 1921. In 1941, Vadim Lashkaryov invented p-n junctions in copper oxide silver sulfide photocells. In 1946, Russell Hall discovered modern junction semiconductor solar cells and patented it. Calvin Souther-Fuller and Gerald Pearson in 1954 demonstrated first photovoltaic cell at Bell Laboratories. In 1958, solar cells were incorporated into Vanguard 1 satellite, after which they became popular. First application of solar cells was in the Vanguard satellite in 1954, where they were used as alternate power source to the primary battery power source. The addition of solar cells on the outer body of the spacecraft lead to extending the mission without any major changes in the satellite or its power sources. After this, large ring-shaped solar arrays were used on Explorer 6, and following this, solar cells became a common feature in spacecrafts. There were 9600 Hoffman solar cells which are integrated in these arrays. By 1960s, solar cells became major power source for the majority of the Earth orbital satellites and other space probes because of their ability to provide best power to weight ratio. The early success of solar cells in spacecrafts can be attributed to expensive power sources, first, expensive power sources could be used. Second, the availability of few alternative power options. C, since cost was not an issue, best possible cells could be used. Spacecraft market led the development of highly efficient solar cells. Later, terrestrial applications of solar cells began to gain attention. Space applications included solar cells built from gallium arsenide based 3,5 semiconductor materials and later involved 3,5 multi-junction cells, whereas terrestrial applications mainly used silicon. Let us next discuss about the research and industrial production, some facts and some figures related to the industrial production. Terrestrial applications of solar cells gained attention with US National Science Foundation's Advanced Solar Energy Research and Development Division driven research applied to national needs program. This gained impetus owing to the oil crisis in 1973, and during this time several solar cell producing firms were established. Example, Exxon, Arco, Shell, etc. These were soon joined by technological industries such as GE, IBM, Tyco, etc. The declining cost of solar cell led to their exponential growth. Figure 6 shows the historical price per watt for silicon cell. Figure 7 shows the learning curve of photovoltaics, that is Swanson's law, and Figure 8 shows the installed photovoltaic capacity worldwide. In 1990s, we can see that the polysilicon cells gained much popularity. The efficiency is lower than that of monosilicon. Nevertheless, the low cost drives the research activities. By 2000, polysilicon cells became prominent in low-cost panel market. However, owing to their low efficiency, monosilicon cells have gained importance. Because of high silicon prices in 2004 to 2008, silicon consumption was lowered. Crystalline silicon panels dominate worldwide markets and are mostly manufactured in China and Taiwan. Solar photovoltaics is growing fastest in Asia, where China and Japan presently account for almost 50% of worldwide installation. Globally installed photovoltaic capacity reached nearly 301 gigawatt in 2016, which supplied 1.3% of the global power by 2016. So students, let us summarize what we have learned in this module. In this module, the working of solar cell was explained. Also, the various parameters influencing the efficiency of solar cell were discussed in this module. In addition, the timeline of the development of material for solar cell was discussed in this module. Finally, the classification of solar cells was demonstrated and various materials for solar cell production was studied. Thank you students for your attention.